Okay, hi everybody. I'm Mary Thomas, and I lead and coordinate a lot of the HPC training events. And I'm really pleased to welcome you all to our Advanced Computing webinar series, or our Advanced HPC. I want to introduce you to Andrea Zanca, who has a background in cosmology. He earned his PhD analyzing cosmic microwave background data from the Planck satellite. He also leads our SDSC Scientific Computing Applications Group, which focuses on helping research groups in any field of science support, benchmark, and optimize their data pipelines to national supercomputing. Andrea has expertise in parallel computing, Python, C++, distributed computing with Python data-intensive computing, Kubernetes cluster administration, and cosmic microwave backgrounds. So with that, I'll turn this over, and I want to thank Andrea for doing this presentation. I think you'll find it very in-depth and detailed, and there'll be a link given for the talk to a GitHub repository that you'll be able to access and work with later on. With that, I'll turn it over to you, Andrea.
Thank you, Mary. Okay, so I'm going to start screen sharing. There we go. Okay. Can someone confirm the screen sharing is working properly?
Confirming.
Okay. Very good. So let's start. So in this tutorial, I'll be showing you some important aspects of using Python in a high-performance computing environment on a supercomputer. I will be running on Expanse, which is our local supercomputer here at the San Diego Supercomputer Center. However, this is very portable. This is all Python packages that run very effectively also on other supercomputers. So you can use very similar techniques to run on any other local or national supercomputer that you have access to. Okay. And in particular, if you are running on Expanse, I am using Galileo. Galileo is this feature. This is a package that allows to basically execute a JupyterLab environment in a computing node. So every time, of course, that we're running on HPC, that we're using a significant amount of data and computing, we want to run on computing nodes. So first thing that you need to understand is look at the documentation of the supercomputer that you're using and understand what's the recommended technique for running a Jupyter Notebook, okay? And Jupyter Notebook is the best environment at the beginning for exploring your data, doing some tests, runs, and develop pieces of your software. And then once you have a recipe that you built in your notebooks, then you can build some Python scripts and do more large-scale computations. But generally, the best way to start using Python, even on HPC, is through the Jupyter Notebook environment. Okay, so in this case, so this is Expanse specific, so I don't want to spend too much time on this. So this is basically a script that you connect to Expanse, you run this on the computing node, and this is going to give you a link. You click on that link and you get access to a JupyterLab environment running on a computing node, okay? Now, once you have your Jupyter Notebook environment running, second thing is how do you handle the Python environments, okay? Again, this is different for each supercomputer, so please look at the documentation. For Expanse, I am recommending two techniques, okay? So you see all the files here on the left. This is the content of the GitHub repository that Cindy pasted in the chat before. So you have access to all of these files and you can try to run them yourself if you have a computing if you have an account on Expanse, or you can run on other machines. So the first technique that I'm showing is so the main concern about using Python on high-performance computing is that a Python installation is composed of thousands of tiny files, okay? And this can cause trouble, especially on the parallel file systems, which are very, like Lustre, which is very common on supercomputer environment because they are optimized for parallel computing, and they work very badly with Python environments. And so there are some techniques to go around that. And the recommended technique on Expanse is to stage a Conda environment. So is to package your Conda environment into a single tar.gz file, okay, into a single package, and then stage that package on the Scratch space, which is a very fast file system because it has solid-state drives, is on solid-state drive, so it's extremely fast. So you can look at the detailed documentation about this, but basically what's doing is whenever you want to run something, so you want to run some Python distributed computing. So in this case, we have some sample test code, which is node info.py, which is just simply printing out some node information. And we want to execute this on multiple nodes. So you see, we are requesting 3 nodes, and we want to run this in parallel at the same time on 3 nodes. But first thing, we need to stage the Conda environment. And so this is what we do. We first stage the Conda environment, and then we execute the script, okay? And this way, each of the 3 nodes is going to unpack the Python environment, which is a Conda environment, which was prepared before, unpack it on the Scratch space, and then run starting from there, so that is Python can run very efficiently, okay? And our Galileo example, our Galileo script already creates those environments. So you just create it once by running Galileo once, and once you have Galileo executed Galileo once, then you can reuse this environment in the future using this technique. Now, the second technique instead is using Singularity. Okay, so Singularity is a software that allows to run Docker containers inside high-performance computing environments. So what you can do is you can build a Docker container with all of your Python requirements, and then you can use that Docker container to run on Expanse. This way, this container is just one single large file, and it's extremely efficient to be handled by the supercomputer, and so you can execute Python in a very efficient way. Okay. So you see, so these are 2 techniques that you can use, and some supercomputers have a home file system which is optimized for Python, and then in those cases you can even just install Conda environment in your home folder, but please check the documentation first to see if that is the case for your system. Okay, after this quick introduction about ways of storing your Python environment, let's get into more of the material. But before that, just a very quick note about AI code assistance. Okay, so nowadays the status of AI code assistance is very advanced, and so even in very very specialized niche software, in advanced science, on any domain of science, you should use a code assistant. Okay, I recommend two different techniques. So you shouldn't write Python directly yourself. So it's extremely important to understand at high level how Python works, what techniques you want to use. But then once you get down to the actual implementation, you should ask a code assistant to implement something for you, and then review that and iteratively between having the assistant code some feature for you, and then you review that, you see if it's as expected, you make sure you're understanding everything that the assistant is doing, and then you can iterate and request improvements to the assistant so that you can together with the support of an assistant, you can get to develop incrementally your code. I recommend
Andrea? Oh,
yes.
I'm sorry to interrupt, but there's a question. Are you running this on your local computer or are you running this on Expanse?
I'm running this on Expanse.
That's what I thought. I wanted to make sure I answered it correctly. Thanks.
Yes. So this is a Jupyter Lab environment, which is executing on Expanse thanks to Galileo, which is this package developed here at SDSC that gives a Jupyter Lab environment. Just executing one command, you're going to get a Jupyter environment running on a computing node. Okay, so I recommend two different code assistants. So the first one is GitHub Copilot, and so this runs inside Visual Studio Code. Okay, and this so these AI environments, they do not run on the supercomputer itself. So you should use the so you should develop your code locally. Okay, once you have a more advanced version of the code, then you can test your runs on the supercomputer, and then you can go back and forth using generally the best way if you use GitHub itself. You have a repository with your software on GitHub, and then you can quickly develop locally, push to GitHub, and then get the latest version of the code on the supercomputer and run on the supercomputer and go back and forth between the local environment and the remote environment by using GitHub. Okay, so Visual Studio Code is an IDE. Okay, so it's like this. It's an interactive development environment. So you can execute notebooks or can execute Python code. And what happens when you use the code assistant is you have a chat, basically like ChatGPT, but embedded in your software environment. Okay, and so here you can chat with the assistant, and you can ask the assistant to make changes to your Jupyter notebooks or to your Python files. For example, here I wanted to create this diagram for this class, for these notebooks, and so I asked the assistant to add a markdown cell that shows the architecture of Dask. Okay, and here you see here I have different LLMs that I can rely on. So generally I use GPT-5, and so I ask GPT-5 to implement this, and GPT-5 is going to contact OpenAI, and then is going to compute, to work on this request, and after a few minutes is going to come back with a modification to your Jupyter notebooks, and then you can test. You can see that works as you are expecting, and then you can just push it inside your repository. Okay, and so I think this is the best alternative, and it's free for academic users, so you don't need to pay anything to have this support from Copilot. Then the second, so this is a family of tools, is the code assistants that work in the terminal. Okay, so so these are similar, but instead of working in your IDE, they work on the terminal. So you see here, for example, again, I'm running the AI assistant locally on my laptop. Okay, and then I can push and pull whenever I need to have this available on the supercomputer. Okay, so here you basically, in your terminal, you run Gemini, and this is going to spawn this custom terminal, which allows you to chat with the assistant and have the assistant make changes for you. For example, here I simply wanted to add in the README at the root of my repository a list of all the subfolders and a summary basically of what each subfolder contains. Okay, so you see, I ask the assistant what to do, and then the assistant is going to look into the folders, understand what each folder is doing, and then it's gonna say, oh, let me edit the README. This is exactly what I asked, and then it's gonna tell me, okay, this is my suggestion. So I want to add these lines that explains what the different folders are doing. So I can review this modification, and then I can just tell the assistant, just, okay, that's good. So commit and push, and then the assistant is going to automatically add the changes to the repository and then push to GitHub. Okay. Okay. Very good. So now let's start with the actual content of the Python for HPC series, but I wanted to introduce those things to you first. Okay. So now I am going through the notebook, which is in the folder 3_threads vs processes. So if you can follow along opening it on GitHub, or if you even want to run it locally, you can fire up your Jupyter Lab or VS Code on your laptop, and you can execute this. So we will be getting into the HPC only content later, and for that one you need a distributed computing environment, but for now you can just run on your laptop. Okay, so the single most important aspect about understanding how to run a distributed computing is the difference between threads and processes. Okay, so when you run a Python execution, okay, by default you only are so by default, if you're just running Python, you are exactly running like process A down here. Okay, so you have one Python process and one thread. Okay, and whenever you have one thread, that means that only one core on your machine can execute calculations. Okay, and this is very inefficient. On Expanse, for example, I have 128 cores. So if I just run one process with one thread, then one process is doing all of the job, and the other 127 are just idle. Okay, so the purpose of multi-threading is to be able to leverage all of the cores that are available on your machine. Okay, if you have a laptop, maybe it's just 4 cores or 6 cores, but still, it could give a good speed up to your computations. Okay, so the best way of achieving this is using multi-threading. So we are in the case over here. So if you configure your software properly, you can split your computation in multiple threads. Okay, so here, for example, we have 4 threads. Now that you have 4 threads, now each thread can run in parallel on its own core of your CPU. Okay, so now potentially you could go 4 times as fast, okay, in the best case scenario. And so if you are on HPC, you have 128 cores or more, and so you can run a lot faster. Okay, but there is a problem with this technique with multi-threading, which is that Python in particular has an implementation detail in the language itself, which is called the global interpreter lock. Okay, the global interpreter lock is a feature of Python that basically is a unique lock that each thread has to acquire whenever it wants to make any change to Python objects. Okay, so that means that even if you have 4 threads, okay, thread 1 is when so imagine thread 1 is executing a Python script line per line, okay, and now has a line where it's doing some computation, is modifying some Python classes or objects, and at that point the thread acquires the lock. So once this thread has acquired the lock, the other threads, they also need the lock to keep executing their code. And so, but the thread number 1 has acquired the lock, so the other 3 cannot execute. So they are waiting for thread 1 to release the lock. Okay, and so this so you get into a race condition when all the threads want the lock, and so one of them is executing at a time. Okay, and so you don't get any speed up. Okay, even if you have 4 threads, there is this other problem, which is the global interpreter lock, which is just allow one of those threads to execute. Okay, and there is a okay, so how do we get around this problem? So this is a big problem in high performance computing with Python. How do we get around this? So there is a workaround because the Python, the global interpreter lock is unique to each Python process. Okay, so a workaround is, oh, why don't we just spawn 4 processes? Okay, and so we have those 4 Python processes, and each of them has a different lock, and so there's no race condition in this situation, and they can process in parallel easily, and they can execute without any problems. Okay, but there is a big problem. There is a big issue with this, is that the memory is separate for each process. So while if you can use multi-threading properly, then it's the good is that the memory space for the process is unique. So let's say that you have a big array memory, and in case number 1, where you have a single process and 4 threads, the threads can access that memory, so they can read a piece of an array, they can write it back, no problem. While in the second case, now you have to copy that array 4 times in each of the process, and so you are wasting some resources because there's duplication. So you're using more memory, you are taking more time. Okay, so every time you use Python and you want to use multiple threads, you have to keep this options in mind. So am I able to use threads, or am I forced to use processes? Okay, so now let's see an actual use case of this. Okay, so So as I told you, I'm running on Expand, so I have 128 cores. Okay, now we are going to go into details about Dask later on, but for now, just trust me. What we are doing here is we have a computationally heavy function, okay, which is computing the Fibonacci sequence for some number n, okay, and we want to execute this many times. So we want to execute this 128 times because just to show that we're doing some parallel computation. Okay, so and if we don't want to, it's going to take a long time to execute them one after the other. So what we want to do is to execute them in parallel. And so this is the first way of executing this in parallel on multiple threads. Okay, so the idea here is we now have 128 threads that each of them is executing this in parallel. Okay. Okay, the problem is that we have some issues with the global interpreter lock. And in fact, you see that, and so as I told you, we can run either this way with multi-threading or two with multiprocessing. So in this case, multiprocessing is beneficial. So you see, we are actually paying the price of the global interpreter lock. So executing the threaded version is a lot slower than the multiprocessing version. Okay, but you see that with Dask is very easy to test both. You just tell Dask, I want to execute this with a threaded scheduler, or I want to execute this with a processes scheduler. And Dask is taking care of spawning multiple threads or spawning multiple processes and do the work for you and return the result if there is, and return your result. Okay. Now, there are
Andrea,
other cases.
Andrea, sorry to interrupt you, but there's an interesting comment from one of the participants about a new Python release and the global interpreter lock. If you want to take a look at that, it's a good question to answer right now.
Yeah.
Next month with the release of 3.14, right below. See it?
Yeah. Okay. Yeah, so fortunately, with scientific computing, a lot of the library are already releasing the global interpreter lock. So it's not already now, whenever you're executing NumPy code or Pandas code or Numba, as we will see later, that's already releasing the global interpreter lock. So a Python release without global interpreter lock is going to be beneficial, very beneficial, but mostly for other applications like, for example, a Django application, or so applications that rely a lot on pure Python code. With scientific applications, we are running so often with scientific library which already released the global interpreter lock. That's probably not going to be a big improvements for scientific computing. But in general, for the global Python ecosystem, it's really great news. Okay, so let me show you now another example. So this, while the other function was very computationally heavy, this one instead is waiting on something. So in this case, it's just sleeping, but this could wait on a network connection or wait for this access. Okay, so whenever you are, so whenever it's not about the raw CPU power, but there are, whenever you don't have a lot of need for accessing the global interpreter lock, because you're just waiting on network or waiting on disk, then threading is always beneficial. Okay, so in general, you always want to try to use the threading scheduler. Okay, unless you find that there are some performance issues, and then you might so if you cannot solve them, then you might try with the processing scheduler. Okay, but always try first with the threading. Okay, and one trick of that is always try to use libraries that release the global interpreter lock, like NumPy and pandas. Okay. 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 Now let me stop after this and ask if there are any questions. I'm going to. So you can unmute yourself and ask a question, or write to the chat. So we want to focus on questions about tasks and threads.
There was a question a while ago about a development environment, and can we install it on Expanse? And I'm trying to find can a user install the GitHub Copilot extension to the VS Code that is installed on the cluster?
No.
No?
No.
Okay.
Unfortunately, VS Code uses too much memory. And so it's not, so even if you use the SSH extension and you run the interface of VS Code locally, and on Expanse or another supercomputer, you are running just the VS Code server. This is not allowed on a computing node on Expanse. However, other supercomputers have different policies. So there are some that allows you to run VS Code server on a compute node. So that's another option you can look at, and that way you have the convenience of a local GitHub, a local VS Code instance, and which is actually executing code on the supercomputer computing node itself.
Yeah, I think you would want to look on the Access website, ACCESS, which is a system it's information about all the HPC resources, and you could find perhaps a machine that hosts that software environment. That's all the questions in the chat. Does anybody have anything they want to ask right now?
Okay, so let's switch to folder number 4. So 4_Numba. Okay, let's start with the basics. Okay, so today I'm going to introduce you 2 Python packages that can help with scientific computing and high-performance computing. And the first one is Numba. So Numba is a just-in-time compiler. So you know that Python is extremely convenient and easy to use, but you pay for that with performance. So compared to compiled languages like C, C++, and Fortran, Python is very slow. Okay, so what Numba is doing is actually compiling your Python functions. So you write a Python function, and then basically you tell Numba, I want this function to be compiled. And so Numba, under the hood, uses some tooling, which is the same tooling used by C++ compilers. So takes your Python, transforms it into an intermediate representation, and then that becomes machine code. And so basically you have a Python function that runs at a speed comparable to C and Fortran without the pain. Okay, so now let's see how you do that. So if you have never used the decorator, a decorator is a way of implicitly calling a function on a function that you define. Okay, so when we do this, so go fast is a standard Python function. Okay, so nothing special about that. But then, if you just above the def, if you write at and then this decorator, what this is going to do is taking the go fast function, passing it to the JIT function. So JIT itself is also a function, your decorator. And then this is going to return another function. Okay, so we have three functions: the original function, go fast, which is a pure Python function. Then GIT, which is a function itself, which takes go fast and produces a special object that is going to provide a very fast version of your function the first time you call it. Okay, and so in practice, so you have your own array. Okay, you have your NumPy array, and then you call go fast, and this is going to compile it. And you know that whenever you're compiling, an issue with compiling is that you need to know the types of everything. Okay, compiling makes a specialized function which specifically works with that kind of input, so a float 32 or an integer or a boolean, something like that. Okay, so that's why Numba has to wait until you call the function with a specific input to know how to compile it. So compiles it on the fly, which is really fast because compiling takes a few microseconds, so you don't really notice. And then, and then you use it like a standard Python function. Okay, and so the technique that you use with Numba is you want to optimize just the most computationally heavy parts of your code. Okay, so you're not taking your code and rewriting completely and starting using Numba from the interface or from the high level functionality of your code. No, the strategy of using Numba is keep everything as it is in your code, read your access your files, your networking and everything. But then once you are in your computationally heavy loop, then you plug this in. Okay, so it's very nice because you can transition from a normal Python code to a Numba powered code incrementally. So you can say, oh, let me just try to optimize this piece of code, which is the most important. Okay, and so the benefits of Numba is not only computational, so that computation runs at C speed instead of Python speed, but also uses a lot less memory. So if you're familiar with NumPy, you know that NumPy is creating a lot of temporary arrays while you're going through your computation. I'm sure that you have the experience of your Python kernel goes out of memory and you don't understand where that memory is coming from. That's probably NumPy that is creating temporary arrays that are then lingering in memory and are driving up your memory consumption. Okay, so Numba also takes care of that for you and creates a very efficient machine code loop that does your data processing and gives you the output without creating unnecessary intermediate arrays. Okay. So, okay, so let's take a look. So you see here, this is testing the Numba optimized version and the Python version. Okay, so you see, yeah, so you see, Python is, yeah, Python is still pretty fast. So you see, still a factor of 20, but they're both quite fast. Okay, so you see here with PyFunc, you can access the underlying pure Python function. Okay, so you see here.
Did you see that, Andrea, there's a question about how Numba compares with Python or Weave for efficiency?
Yes. So as for, so I haven't used Weave in a long time, so I don't have a clear picture in mind. But as for Python, the speed is comparable. So they both basically give you back machine code, and usually I recommend always using Numba because it is easier to use, so you gain in development speed, but and I recommend Python only if you are interfacing with existing C library, and so you don't have, unfortunately, that capability in Numba. So Numba is good when you are in a pure Python NumPy computations, okay? If inside your computations you are calling an underlying C library, then Numba cannot help you, so you need to use Python. Okay, yeah, yeah, and another great feature of Numba is automatic parallelism that we see later, and that's also an advantage over Python. So I think if you have the possibility of so if you do not need custom C code, if you don't need calling underlying existing C libraries, then I recommend you use Numba instead of Python. But yeah, performance-wise, they are very, very similar. Okay, and you can also call a JIT optimized function from another JIT optimized function. So you see here, I have two functions, and I add the decorator to both of them. And now they are both compiled to machine code, and you can call one from the other. Okay, so this just helps you organize your code better. But you see, once the function is Numba optimized, I mean, from the user perspective, it really doesn't look different from a normal function. So it's a very convenient way of squeezing the most amount of performance from a single machine. Okay, then we see how you want to parallelize on multiple machines. But the first step is you don't want to parallelize on multiple machines a code which is very slow on a single machine. So first step is optimize locally, and you can even do this on your laptop to benchmark different parts of your code and try to improve performance. And then once you know that your code is already running as fast as you can, then you can work on parallelism. Okay. Is there any questions on the basics of Numba?
Yeah, there is one question, Andrea. Can you see that question?
Yes, so nowadays, yeah, you can disable no Python. I mean, you lose most of the performance of Numba if you use no Python. So yeah, so you can check if you gain anything by doing no Python equals false, but generally you don't gain much. So you have to, yeah, maybe you can see if you can maybe if you can re-implement the SciPy function in pure NumPy, for example, or if not, yeah, there's not much you can do, unfortunately. If you're relying on a big SciPy library, then Numba is not going to give you much speed up. So my suggestion is try to so make sure that you are passing to the SciPy library a large amount of data all at the same time, so that you can really leverage the performance improvements inside the library, not looping too much on Python before calling SciPy. So you want to get your data to SciPy as quickly as possible. Okay, is there any other question?
No, I don't see any new questions. Thank you.
Okay, so let's go. Yes, so let's just go a little bit deeper in using. So the Python functions that you develop and then you want to give to Numba, they can use NumPy functions, and most, I think 95% or something, functionality of NumPy is supported by Numba. Okay. And one important thing to understand is that Numba is not actually using NumPy for real. So you just implement functions in NumPy to basically explain Numba what's the work that needs to be done. And then Numba is going to bypass NumPy and directly could go and call the low-level math libraries. So even NumPy, for most of the most critical operation, is calling some optimized BLAS implementation, some optimized library implementation. And Numba is bypassing that, just calling the underlying very optimized compiled libraries underneath. But still, it's still extremely useful because you can develop your function without, so you start without the decorator, you develop your function, you test it, make sure that's working as expected, and then you add the just-in-time compilation and you make sure that it's still working as expected. Okay. And so you see, you can do conditionals, you can use any specific function, assignments, and so on. And so you see that, so inside this object, Numba is actually storing different compiled versions of your function. So with integers, with floats, and so on. Okay. Here we're just looking at different the speed that you get with different implementations, but yeah, we don't. Yeah, it's not very important. And I'm going to skip creating new functions. That is not very interesting, but you can look at it on your own if you think you might be interested. I think the most important topic that I wanted to cover about Numba is going to be multi-threading. Okay, so as we were talking before, we want to release the global interpreter lock, but also an important thing is that Numba can do multi-threading for you. So and it's all has a parallel equal true arguments that is going to use some heuristics inside the code to understand how to parallelize your code. So, and also support some more complicated functions. So even if you have some reduction of your, for example, you want to sum, you want to compute some computation, then you want to sum the results of your computation. That's also parallelized by Numba. So Numba is going to use multiple threads in the parallel part of your code, and then is going to as each thread finishes their job, is going to accumulate everything into the output variable, and then it's going to return that variable. Okay. So so you see, this looks kind of magic, and as all kind of magic, sometimes it doesn't work. So And if it doesn't work, it's going to give you an error that tells you why it is failing. Okay, so you want to try this first on maybe a simplified version of your code. Try to understand how to make this parallel, and then make the code more complicated so that you understand step by step if Numba can work for you in your situation or if not. Okay, so you see here, for example, that we're calling a mean. So even this, so this is one of those situations where you need to implement it properly, otherwise there are race conditions where parts of the code are executed out of order, and so that's why having a parallel computing library like Numba, that a multi-threading library like Numba can help you so that you don't have to think too much about those details, and let Numba take care of that. And a very useful Jupyter magic function that you want to use when you're using multi-threading is time. So if you do %time, this is going to execute the Python code, and then it's going to give you so you see the difference between time it and time. So time it is specifically for repeating the computation many times to give you a very precise estimate of the speed of your computation, of the time taken. Time just executes once, but a very important thing that you want to do is you want to compare CPU time and with wall time. Okay, so CPU times is how much each, so the overall time over all the cores that you are using. Okay, so so you see, when they are very similar, that means that there is no multi-threading at all. So there is one core which is executing all of your computation. Okay, so this is not multi-threaded. Okay, because we put parallel equal false. But if you have parallel equals true, you see computation took 6 milliseconds, but in those 6 milliseconds, we used 700, let's say for simplifying, 600 milliseconds. That means that about 100 cores that were executing at the same time. Okay, so this is a great way of understanding how much how your computation is running. So here we are basically parallelizing 100 times. Okay, still you don't get 100 times the speed up. Okay, time is just going from 19 to 6. So of course, the theoretical 100x speed up can be achieved only in specific situations. Okay. And then here is, I told you about doing parallel equal true for automatically have Numba taking care of everything. If you want to be more explicit and you want to tell Numba where to parallelize, then you want to use p-range. Okay, but this is not a very important topic, so I don't want to dig into this right now. Is there any question on using multiple threads with Numba? So we are still speaking about running your code on a single machine. Okay, but instead of running at Python speed, we run at C speed. Instead of running on one core, we run on multiple cores. Okay.
There was one question that Robin, Kyle asked and Robin helped out with, but if you want to take a look at this one there that you're looking at, Kyle asked if can you disable no Python or otherwise allow yourself to use other things like some complicated SciPy function. So
yeah.
that was...
No, I agree with the answer. Thank you very much. Okay. Very good. If there's no other question, let me get to Dask.
We have one more question. Upala asked this. There you go, that bottom one. if we run a pipeline?
Yeah, so OMP num threads, so it depends on your environment. Most of the time is automatic, and automatically Numba is going to use the same number of threads as the existing cores on your machines. So generally, if you want to use all the cores, you don't need to do that, okay? But if you want to use less, then you should set OMP num threads. So let's say you have 128 cores, but maybe you want to use just half of that because your code is not parallelizing very well, and then you set that environment variable. Okay, so let's switch to Dask. Okay, so Dask compared to Numba, so Dask is a distributed computing framework, okay? So Dask gives you the capability of running on multiple nodes, okay? So basically, instead of running just on this single node as we are doing now, in this single node where my Jupyter notebook is running, we want to launch Dask worker processes on different nodes. So we're gonna launch a separate Slurm job that's executing the workers, and then we're going to have them execute some jobs, okay? So with this, you could use maybe 10 nodes at the same time. So you can leverage a lot of memory, a lot of RAM, and you can leverage a lot of CPU. So this is for increasing the scale of your computing. A larger Dask is a great option because automates a lot of the underlying communication aspects that instead, if you are using, for example, MPI, so MPI is an MPI for Pi package, which is extremely low level. So I think that with Python, you want to leverage these high-level capabilities that allow you to describe a very complicated computation in a very simple way, and you want to delegate to the automatic functions of a package like Dask to handle the job dependencies and data transfer and synchronization between the tasks. So you want to rely on a library that can do that for you. Okay, so Dask. One of the probably the best feature of Dask is so now it's already noon, so I'm gonna go ahead another 15, maybe 20 minutes, and then I'm gonna leave the last 10 minutes for Q&A, for questions. Because I mean, we've taken just some questions while we were going. Okay, so you see, a key aspect of parallel computation is the relationship between the different tasks, okay? So whenever you have a computation, you have different steps, and those steps depend one to the other, okay? And so the only way of computing properly in parallel is keeping track of that, okay? And this is a very general concept, so it's really good if you learn Dask and if you understand these ports to any other parallel computing system. Okay, and so Dask, whenever you call some Dask commands, and in this case, we are using Dask array. So Dask array is a sub package of Dask, which gives you an interface which is extremely similar to NumPy, but allows you to run in parallel. Okay, so let's take a look. So you see here, I just called once. Okay, so this creates an array of ones, and then I am doing a computation like I would do in NumPy. Okay, but you see, yeah, for example, let's take a look at this Dask graph. Okay, so this is a direct acyclic graph. So it's a graph and has arrows, and these arrows point to the flow of computation. And so whenever you have separate columns like this, that means that this is part of the code that can run in parallel, okay? So you see here, whenever we run with Dask compared to NumPy, we need to specify the chunk size, okay? This is tells us basically what's the minimum unit of computation. And so now, instead of thinking of our array as a single array of 15 elements, we have 3 arrays of 5 elements. And so whenever we want to compute something, we can compute them in parallel, one array at a time. So we can leverage multiple tasks, multiple threads on your machine. And those threads can be executed by multiple cores so that you can speed up your computation. And so here you see we are doing, so we are creating the array of ones, and then we are calling add, because we are adding one, okay? And this is running in parallel on 3 threads. And then we call sum, but first we sum locally, right? We sum, each thread is summing its own 5 elements, and then transferring the sum to be aggregated, and then the 3 sums are summed together and this come back. So you see, even here, there is communication, there is coordination between the threads. But this is, you don't care about this. This is handled automatically by Dask. You just tell Dask what to do, and then Dask is going to execute it, taking care of all that. And I wanted to show you how the graph becomes very complicated very fast. So this is just a simple matrix computation. So just dot products, transpose or something. Okay, you see how it becomes really complicated. But good news is you don't have to take care of this yourself, because Dask is doing it for you. Okay. Okay, and you see, there is another interface if you just call your object .dask, where you can look at each step of your computation, what's the data size. Okay, so you see here is a 3D array with 15, 15, and 3, and you can, so so all of these are great user interface functionality that helps you understand your distributed computation, because distributed computing is hard. So sometimes you think your computation is doing something while it's doing something else. So you can dig. Dask gives you all this capability of digging inside your computation and understand really what is going on. Okay, let me show you delayed, and then we're going to stop for questions. Okay, so I saw you here how you can use a simple way of using Dask array. Now let's use a kind of lower level functionality of Dask, but which is extremely flexible. Okay, so basically, let's say that you have a bunch of files. Okay, and you wanna read those files. You have this processing that you want to apply to each single file. Okay, and what you can do with Dask is, let's run all of them in parallel at the same time. Okay, and so what you are going to do is basically you take your normal Python function and you call delayed on that. Okay, you see I call delayed on process file. This gives me back another function, but this other function is asynchronous. Okay, so this other function can run in parallel Okay, so instead of running one, and then instead of executing the first, then executing the second, and then executing the third, okay? This is a simple way of running multiple functions that you have defined in parallel. Okay, so you see this very simple graph. So you process, and there is also an aggregation step. Dask. Okay, so you see another feature of Dask is that it is lazy. So whenever you call Dask.delayed or Dask array, Dask data frame, whatever you call, is just under the hood is building the dependency graph for you, but then is only execute when you explicitly say Dask compute. Okay, and so at that point is actually being executed. Okay, so you see here that basically what I'm doing is I'm taking, I want to process them in parallel. Okay, but once I process them in parallel, I want to take their results and sum. Okay, each of them is doing a word count, and so you call sum, but you need an asynchronous sum, and that's why you call task.delayed as well here. And then you can execute it. Or you can call dask.compute and execute this computation. Okay, the same thing we did over here, dask.compute. Okay, okay, and we are still working on a single machine.
I only have one question from our.
Yeah, so the visualization, you need a package for the JavaScript visualization, which is this one. So if you're running locally, you should have this function so that the JavaScript should work. Okay. If it still doesn't work, please open an issue on the repository and I can help you after the tutorial. Okay, is there any question on Dask delayed? So Dask delayed is very flexible. So for example, something you could do is overlap computing and data access. So if you are reading a file and processing it, reading a second file and process it, you can achieve pretty easily. You could process the first file, and in the background, you could load the second file, so that while you're doing the computation, you're also doing the disk access, so you save time. And this you can achieve with Dask compute. So Dask delayed, you're running on a Slurm array jobs. It just allows you to do trivially parallel tasks. So each of the Slurm jobs is executing independently, and they don't coordinate at all with each other. While with delayed, you can do, you can coordinate, you can you can chain multiple functions one after the other, and handle dependencies between different tasks. Okay, so let's say that can execute more complicated computations that you can do with Slurm arrays. Yes, it's kind of similar to SnakeMake workflow. Yes, you can achieve something similar with SnakeMake. Yeah. Dask is more flexible. You are implementing it yourself, so you have some more wheels to turn, while SnakeMake gives you more probably simpler interface to some tasks, but not as flexible as Dask delay. Yeah, exactly. Dask is automatically doing the processing for you. So you just tell it, oh, do the first. So whenever you are executing one, load the second, and then you tell it, oh, when you have loaded the second, wait for the computation on the first one to work, and then it's going to do it for you. Okay, I'm sorry, we are a bit short on time, so let's go to array, to the last, we have the last three notebooks. Okay, so Dask array, yeah, this is a very simple example of viewing Dask array and comparing how you use Numba, Dask array, and NumPy. Okay, so I have this, I have a single computation. Okay, so you see how we do it. If you have a computation, this is a big, very large matrix, and we do a bunch of computation on that matrix using NumPy. And if we want to use, step one is let's use Numba. So Numba, really easy. You take the function, you give it to Numba, and Numba is going to optimize it for you. And now you have a separate function, which is just in time compiled, so runs very fast. Okay. With Dask instead is a bit different. So what you do with Dask is basically every time you call a NumPy function, now you call a Dask array function. So you see now instead of np.syn, np.log, I have da.log and da.syn. So those functions are already aware of the of the distributed computing situation, and so can leverage multiple workers working on this. Okay, so you see how NumPy is very slow. So even NumPy is running C code, right? NumPy is implemented in C, so under the hood is really fast. But you see, whenever you're doing a NumPy computation, you're going into C and out, in and out. And every time you go in and out, NumPy needs an array where to store the output, okay? And so it's going to create a lot of temporary arrays, and so it's very efficient. So it takes 33 seconds. So the same function with Numba takes just 1 second, okay? And this is also using some parallel computing, and even better, it's using less memory, okay? Because it's not creating any temporary array. So it's basically taking one element at a time, computing the log, multiplying for this, multiplying with the sum, and all of that, and writing to the output function, and then loop through the array, and that's it, okay? While NumPy is going to take A, give it to NumPy, get back an array of the log of A. Then it's going to do the same with the sign, the same with the square. Now you have a bunch of arrays. And then it's going to multiply all those arrays together, so it's inefficient. So the same computation you can do with Dask, and it's actually not too bad. It's just a little. So the difference is that Dask is going to take small chunks and do the quick computations in parallel on all the chunks, and then aggregate everything at the end. Okay, so you are paying a bit the price because so still it's not as fast as Numba. Okay, but the big advantage of Dask is that this can run on multiple machines. So if your data doesn't fit in memory, then Numba cannot help you much. You need Dask. So it's good to see that Dask is pretty efficient as well, because when you want to jump from one machine to multiple machines, you have to go with Dask. Okay, and actually the best is to leverage both. So you can do a distributed computation with Dask, but then each individual, so on each node you are executing some Numba code. Okay, Okay, so you should start at the beginning, play with Numba first. Then once you gain some speed up, start looking into Dask. So the big difference between the two is that while you can transform a code incrementally using Numba, you cannot do that with Dask. So if you want to run with Dask, you have to basically rewrite your code to use Dask. Okay, but the benefit can be really large and can allow you to process data that doesn't fit in memory. So let's switch to notebook number 3. So in this case, we have a situation where array.
Andrea, real quick, I think we're getting a few questions, but I'm going to suggest we hold them till you're done with your material.
Yes, also because they look pretty detailed. So I
Just
can
keep
stay
asking,
here
guys.
after 12:30 to answer those questions, which are very detailed. And for now, I'm going to finish this content. Okay. And so another intermediate situation is where you are still on a single node, but your data doesn't fit in memory. And so what you want to do is Dask allows you to basically stream through your data. So if your data is on disk, you can load a piece of your array, do the processing, write the result, and clear up memory, and then use the memory for something else. So here, for example, I have 128 gigabytes of RAM, I think, on Expanse or something like that. But I'm processing 300 gigabytes, okay? And I can do that because Numba is automatically loading just a subset of your data, just a number of chunks, run the execution, and then flush away the memory so that you can reuse the memory again. Okay. And now let's get to the last topic of today, which is finally running on a multiple machines, so multiple nodes. And so the good news is that the interface is the same. Okay, so from the user perspective, you're just calling Dask function, and Dask is going to automatically handle the distributed part of the computations for you. Okay, so first of all, we are stepping in something which is more complicated. So we need we need a process that can coordinate your jobs, and this is the scheduler. So you see, I am in my computing node, so now I am co-located in the same machine, which is running my Jupyter notebook, and I'm launching this scheduler. Okay, again, the code for this is all on GitHub. And now the scheduler is going to coordinate my jobs. Okay, so what you do is you run this cell, which is telling Dask that we are using the distributed scheduler. Okay, so you see, whenever you call this, now the notebook is going to connect to your scheduler so that can leverage the workers that we are going to launch pretty soon. Okay, so so see how you describe your computation. It's exactly the same as before. Okay, so look at this. You are telling Dask what's the chunk size. Okay, so the only difference between this and the one before is this cell here. Okay, so whenever you execute this code, any Dask call that happens after is going to be, instead of running locally, so the one we did before, it was running in the same machine. Now, nothing is running locally. So when you run, so you see here the scheduler that's saying I have a connection to something. This means, oh, you see here, a receive client connection. So the client is connected to the scheduler, okay? Now, if I execute the compute, the client, so the notebook, is sending the jobs to our scheduler, okay? And we can look by looking at the dashboard, okay? So this is one of the extremely useful features of Dask is the dashboard, okay? So you see, this is my notebook, and I have this link here, which is basically connected to some specific port. And in that port, here is a real-time view of your distributed computation. So this is not something this is a great insight of your parallel computation, because you can look at what's going on. So you see here, down at bottom right, you see 0/400. So those are all the tasks that we passed from the client to the scheduler, but the scheduler doesn't have any worker, so nobody can execute this. So everything is stopped, okay? So now what we're going to do is we need to give some computational power to the scheduler, and we do that with by launching a separate job. Okay, so we go into Dask Slurm, and you see there is a Dask workers.slurm script. Okay. This is going to launch a So you see now, this is Galileo. This is my session, my Jupyter session. I have a separate job of 2 nodes. Okay, once they get through the queue, that should take just a minute or two. They are going to be available to our scheduler, and then the scheduler is going to execute those tasks. All right. Okay. So we can okay, we can take a look at our dashboard, and we will see the jobs coming in. And once they execute, the most important view is task stream here at the top right. So this task stream is going, basically every horizontal line that we'll see appearing is a separate thread on a worker, okay? And so in our case, we have 2 workers. Each worker has 128 threads, okay? And so we are going to have 256 lines here that show us in real time what each task is doing. And this allows you to understand how the computation is executing. For example, if we have one task only which is highlighted and everything else is white, that means that there is some problem in our code and only one task is executing. And so maybe that's a hint that we have a problem with the global interpreter lock, or something else. Or we can also see what time is spent in different parts of your computation, and that's really difficult to do in a distributed computing environment. So that's a great insight into your computation. And you can dig deeper Here, for example, if you click on the workers, once the workers come out, you can check their memory usage, CPU usage, so that you see if you are running, if your computation is running fine or not. Okay, so this was the last part of the tutorial, and so we can enter the Q&A session, and then hopefully the job is going to go through, and so I can see, I can show you the live view of the dashboard, but or you can do it yourself on your machine. So this dashboard is enabled by the distributed scheduler. So make sure that you look at the Dask documentation. Dask is explaining very well all the different steps. You execute your distributed scheduler, you connect to it, and then you have access to this very useful dashboard. Okay, thank you very much. So we are on top of the time that we allocated. So I'm gonna stay on and answer the questions. So if you have more questions, you can stay on. Otherwise, if you have other appointments, please feel free to disconnect.